back, everybody. Just a quick reminder, we have a midterm on Friday. I don't want to lull you into not studying. I want to tell you it's going to be really hard to study as much as possible because I just think that's good practice. But it's not meant to be a terrible exam. Like on the final, I might ask you a hard question or two. But really, it's going to be very homework-esque, the stuff that we've covered. People have asked me in this class if I'm going to have any tough integrals. And the answer is no. So I won't do anything that you have to integrate that isn't like fairly obvious. So if you can't integrate a polynomial, that would be a problem. So there might be some integrations, but I want to test on statistical concepts and not how awesome your calculus is. Because I know sometimes people forget exactly how to do like integration by partial fractions, or they're not as fast, and that could soak up a half hour just reminding yourself how to do it. So I'll try to get rid of that and focus on statistical concepts. So in the review session, it's kind of daunting sometimes because the problem can take like an hour to do. We're sitting at home, it can take 4 hours to do. I really like that for practice. It builds you up, but I don't want to test you on that stuff. So it's going to be fairly reasonable. I don't want to say easy, but it's kind of at what you might expect is reasonable to. And so the second midterm will get a little bit steeper, and on the final will get a little bit steeper than that. Okay, so the typical sort of ramp. Okay. We will do yes, no, maybes tomorrow during review session, so you can just ask me. And we'll try to hone in on the exam. I'll have the exam decided and made by the time we do that. So it won't be if you ask and I say maybe, then I remove it. So there won't be anything like that. I don't have any strategy other than to try to be transparent. Cool. I want to talk about the project real quickly. This isn't due for a few weeks, so you have time. I'm not going to extend the deadline on this. So I want you to start early, and that's the key to finishing. And so here's the project. This is online. You're familiar with this Bernoulli model, so I just write it down again. I tell you what the mean is. I tell you what the variance of X bar is. So X bar is the MLE. It's a lot of good estimators, and a lot of people would use X bar as their estimator. The Bayesian uses a penalized version of X bar, so it's kind of similar. So what I want you to do is, in part A, is basically verify the delta method and show that as n goes higher and higher, the approximation from the delta method becomes better and better. So this is just a verification of the probabilistic statement of the delta method. So what I want you to do is I want you to collect a whole bunch of X bars right here out of different data sets with varying n and p. So I think I say n is big in this example. I want you to repeat this a whole bunch of times, and I think I have you do this for various n's, so you can see how well this works. I'm going to have you do this for a pretty easy p to start with, so just one version of p, and this result will kick in really quickly. So what I want you to do is draw a histogram with all these 5,000 samples that you're collecting. Draw them. They should look normally distributed. Which normal does it look like? It looks like this one. So you're allowed to use p here. Keep in mind the variance of xi. I'm writing it that way, that this is really a function of p. It's not a function of xi's. So I want you to take this density and overlay it on your histogram and show that it's about the same. As n goes higher and higher, that histogram approximation is really close to the normal distribution. So you'd just be drawing a normal PDF over a histogram. It's relatively straightforward. Problem 2, I want you to do the delta method the way you would do it using it as an inferential technique. So instead of using the actual true p in this calculation, you're going to use p hat. And p hat is X bar in this case. So I'm going to change the notation like 6 times in this homework assignment. That's half of what I want you to just be flexible with, is all the varying notations you could use to convey the same idea. And so this is intentional that I've kind of minced the notations. The expectation is p hat over 1 minus p hat if we're trying to estimate the odds. And that's the problem that we will move to. So estimating X bar is easy. Estimating the odds is a little bit harder. just because you have an X bar in the downstairs, and it kind of messes up some of the asymptotics of everything. And potentially, X bar could be 1 if P was really big, and 1 minus X bar is going to be 1, and you're going to divide by 0, and that's going to tell us the method fails. And we probably should be honest about that and say how often the method fails. So the variance is this. This is a different way of writing down the variance right here, where I compute this thing, the G prime squared. G prime is just the odds of everything. You've got this variance, so the N appears here in everything. So P hat times 1 minus P hat divided by N. And then I'm going to evaluate P and P hat right here. So I guess this was P times 1 minus P divided by N. And then I'm going to substitute in the P hat. And that's what this notation means right here. So anywhere you see a P in the equation, substitute in P hat. Now it's an inferential technique. So what I want you to do is just collect a whole bunch of different data sets under variant N and P. Here's all the different configurations. So there's 4 configurations of N, and there are 7 configurations of P. So there's 28 different combinations of data sets that you'll create. I want you to use the exact same data sets when you compare the 3 different methods. If you re-simulate the data set for all the 3 methods, on average, you'll be telling us what happens, but you won't be telling us conditionally what happens with each specific data set. So I think if you cranked up the number of iterations and the number of times you did things, everything would converge into each other. I won't be able to tell the difference by eyeballing it. So very unlikely unless I go in and make sure it's failed the exact same number of times. We're not going to be that careful in our grading. But I do want you to do it probably the right way. So you need to store the configurations for the different combinations of N and P. So ultimately what I want you to do is just report these expectations and variance estimates. This could be a good idea, this might not be a good idea, to just report this stuff. And I kind of leave that as a caveat, that expectations and variances aren't the end-all be-all. So in this assignment, I asked you to compare the expectation estimates and variance estimates from the different procedures to each other. Again, we're not estimating X bar, we're going to try to estimate, we're not estimating P, we're trying to estimate P over 1 minus P. So I want you to repeat this exercise a whole bunch of times, and probably what I want you to do is plot some box plots of your expectations and variances. So there's a little bit up to your imagination and what to report back. What is the important thing to compare? And I don't fully tell you what to do, I just tell you expectations and variances, but again, that might not be the best thing to compare. I want you to do the same thing with bootstrapping, so under those same 28 configurations, and we're repeating those over and over and over again. So for the 28 configurations, you're running that a bunch of times. How many times? 100 times for each one. So there's some notes in here of how many times I want you to do things. If you want to crank that up to 1,000, go ahead. So, shouldn't hurt. So you can do bootstrapping right here. So your function G, again, is the odds. So you can just do bootstrapping, and so you're going to get one of the data sets, and you're just going to bootstrap over it. And so if you got a data set of all zeros or all ones, bootstrapping doesn't really help you do anything. So that could be a problem and where this might fail. So for small n and small p, or small n and big P, this technique might not be very good. And so if it does fail, and you're plotting some box plots and showing the results when it works, that's okay, but also tell us how many times the technique fails. You probably want to report that back. Where do you write that in the plot? I don't know. I might write it right over the box plot. I might put it in the caption, something like that. So you're going to have a bunch of side-by-side box plots probably in this. And then I want you to do the Bayesian thing right here. So Bayesian analysis is going to come up with a distribution for the odds. And I tell you how to form that. If you want to know what the distribution of the odds is, it's called beta prime distribution. And if you know about the beta prime distribution, you don't need to do a full Monte Carlo simulation. So that's just a hint for you. If you know about the beta prime distribution, i.e. you look at Wikipedia, and you look at what its mean and variance are, you don't have to do a Monte Carlo simulation to estimate those two things, and that would be fair game. I want to just kind of leave that in there, so I do say in the description to do this brute force and lots of Monte Carlo, and if somebody wants to shortcut and say, I've got an exact estimate that I get from Wikipedia, and I know the expectation and variance, so for each of the data sets, I can summarize it by probably X bar to estimate the keys, and then I just have to figure out what the entries are to compute the expectation and the variance. The alpha and beta that they talk about in here are the exact same alpha and beta in a beta distribution. So when they give you the functional form of the expectation and variance for the beta prime distribution, those alpha and betas do have the exact same meaning of in the beta distribution. So it's going to be sum of the xi's plus alpha, whatever your hyperparameter is, and then the n minus sum of the xi's plus beta. So that's going to be your updated version, just like in the beta distribution. And so I want you to basically choose some prior. I kind of say maybe choose the half-half prior, and then compute all the expectations and variances from that beta prime distribution and compare the Bayesian results. So I want you to compare bootstrap, delta, and Bayes to each other. So you might have in one set of box plots all the expectations from the 3 different results right next to each other. You can see how they vary next to each other. What you'll notice is if you use the beta half-half prior, the expectation isn't always defined in the beta distribution. And for me, that's not a big deal because the whole posterior does exist. So maybe it's just telling us the expectation isn't always the right statistic to present to people. I want to point out for the delta method, you don't have a choice. You have to report the expectation and the variance. Those are the only things that characterize that distribution. But for a beta prime distribution, instead of using the expectation, you might end up using the MAP estimator, the maximum a posteriori estimator. So, and that always exists. And so you can just make some comments at the end. This simulation study is not working well for Bayes. It works a little bit better maybe than some of the other techniques, but the Bayesian isn't forced to use the expectation. They could use some other statistic. So we could change this and come up with interval estimates and see how often they cover the true answer, and maybe I should have done that. And you would find out that the Bayesian is a better frequentist than any of these other 2 methods. So I don't tell you you have to do that, but we can talk about this in an upcoming review session and see all the different things we can report. The reason I like to leave this a little bit open-ended because this is what research is. You have to decide what to compare and how to compare it. So I give you kind of a tacky way of doing the comparisons with expectations and variances. So the Bayesian could do things that a frequentist does with their Bayesian model. And you could do the same thing up here, and maybe I should have changed the assignment to do that, but I want to make several points at once. Another thing you could do for the Bayesian answer to make sure the expectation always exists is you could crank up these numbers in the hyperparameters for the beta, so you could make this a beta 2,2, and the expectation will always exist. That's a terrible answer because you're putting too much bias into things. Okay, it's not a terrible answer, it's not what I would do. So, because I would be doing something to define an expectation in all cases where it's not really the right prior to use. It doesn't have properties other than making my life convenient for arbitrary reasons. So, you could, if you want to shortcut the problem, just say, well, I made it a beta 2,2, and it biases things a little bit too much for small n. And that would be a fine answer. At least you've made a comparison and you're able to conclude some stuff about these 3 methods. So I don't think it's good enough to just do a couple probability problems in the book. I think you want to experience how all these techniques work. So what I really want you to do is experience it. Run through that sim study and hit repeat a whole bunch of times, see what happens, make some graphics, and then write up a couple page report on it. Okay, it looks like a lot. It can be done in a streamlined fashion to save you some time, but I think this will take at least 20 hours. So start early. So I would say if you want to start real early, just do part A. So do this one. That should be a good thing to do over the break. And then maybe start on problem 2 and store all those data sets. And if you have that, you're almost done. Because you don't actually have to do any real math to finish all of this. You just have to use those samples in the correct way. Of course, you're going to get a bug in your code in the last minute. So if you start on March 21st, you go, it's not working, I don't know what's wrong. So, and you're in a panic. I'm gonna say let this be a learning experience for you. So start early. So keep in mind when you start early, you finish early, and you spend the same amount of time doing things, but in a non-stressful way. Okay, so we'll talk more about this, and you've got 3 weeks to get this done. I don't think it's too overwhelming. Any questions about that?
So we're doing a report on this?
Yeah.
So just write up a little bit about our findings.
Yeah,
Graphics and stuff.
Graphics and stuff. It alludes to what I'd like to see in the write-up. So I'd say read through it, make sure you're organized in your thinking. Personally, every time I got a homework assignment when I was in grad school and college, even though I wanted to just put it in my bag and forget about it until later, I already know it's a better idea to just read through it right away so you can be walking around thinking about it. So get over that stressful hump as early as possible. I get anxiety when I open my email account, and I know I need to open it more often so I can get to all the emails I have to do, instead of just freaking out about it. So I feel the same way you guys do, so I start early. Okay, sounds good. Do some factorization theorem. We'll look at that example on that side of the board in a moment. That's just a normal example. And all we're trying to do is infer mu right here. We'll let sigma squared be fixed. And I'll make a few points about that. We left off here last time. So the factorization theorem states that if this factorization exists, which is a factor including the sufficient statistic and theta, right here, I should say, if this factorization exists, it tells us Tx is sufficient, and if Tx is sufficient, it tells us that the factorization exists. So we've already done one correction of this proof. If Tx is sufficient, then I can just write this thing down. This is a true statement, no matter what that statistic is. That doesn't need to be sufficient. And that doesn't need to be sufficient to write this thing down right here. But the neat part is this part cancels out if Tx is sufficient. That's if Tx is sufficient. That's telling you this conditional distribution is not a function of that parameter. What is that conditional distribution? That conditional distribution is the ratio of the distribution of the data compared to the distribution of the sufficient statistic. They have the same shapes, that's how I think about it, and so we get a lot of cancellation and all of that. And then you're left with some function that just depends on the data. Right here, we'll call this h of x. This is just a function of the data. If I can compute x, I can compute t of x. And this right here would be your function of the sufficient statistic and the parameter. So factorization is this, right here. Let's do the other direction, just real quickly. So I want to kind of point out, when I'm thinking about an example, I'm thinking about what can I factorize out away from mu. So I'm just kind of eyeballing it when I'm recognizing what a sufficient statistic is. I'm kind of employing the factorization theorem in my head. And so I kind of notice when I write this whole thing out right here, and I haven't fully expanded this, but that's a normal distribution. We come down here and I can kind of lump terms in terms of the parameter mu. So I want to kind of point out, when I drag this sum inside right here, this term right here will go to 0. So if I sum up the xi's minus x bar, the sum of xi's minus x bar is 0. So this term is 0. Once I drag the sum in here, this doesn't have any mu's in here, right here. I'll point out you can never untangle that from the sigma. So if sigma squared was a parameter of interest, we know that that always goes hand in hand with it. So it's telling us right away that this part has something to do with the sufficient statistic for sigma squared, or sigma itself. This part right here, you'll never be able to untangle x bar from mu. It's always going to be next to it. So if you want to expand that out, you're going to have this term in the cross term. The x bar and the mu will be next to each other, and you can never get rid of them from each other. So it's basically what part of the data is always tangled up with that parameter, and you can't factorize it away. And that's telling you what's sufficient. So kind of at a glance, I can tell by looking at that, I can never untangle x bar from mu, so x bar is sufficient. I could say something like, well, I can never untangle xi's from the mu either, so I can't untangle all the data from the parameter. So the whole data set is sufficient too. Later on, we'll get into the definition of a minimal sufficient statistic, and it's a carryover from the definition of a sufficient statistic. We'll look at that when we come back. But this is one-dimensional, and the whole vector of data is n-dimensional, so there is a minimal compression of that. And it wouldn't be hard to convince you that you can't compress it any farther than one dimension.
If we were to think of like, for some reason, like the min-order statistic is sufficient, does that mean just that the whole data is sufficient because you would have had to order it?
Yeah, you're thinking of like a Cauchy example or something like that. Yeah, exactly. So this problem in the book that says, show that for a location scale family, is this the problem that you're having in your mind? That the data set itself or the order statistics are sufficient. So here's an example where it's a location scale family, and x bar and s squared are the sufficient statistics, but if you go to a Cauchy example, a counter example of that, there's no way you can factorize everything. So some location scale families have minimal compressions, but in general, over the whole thing, the Cauchy distribution is a good example of this. That's one where you cannot compress everything into a lower dimensional form of the sufficient statistics. So when people are saying the order statistics are the sufficient statistics, they're saying the data is sufficient and it's exchangeable. So because it's IID. So it's putting all that stuff together. Yeah, that problem is kind of confusing because the normal example is one where the order statistic, it is sufficient, but there is a more reduced form of that sufficient statistic. But mathematicians always like to generalize, so in general, they're talking about all the cases out there. That there might, even if there's one case out there that doesn't have the minimal compression into something that's reduced, that means in general it's not true. So I'd say the answer for that homework problem is just think about a T1 or a Cauchy. Cool. Okay, any other questions? Good question. Let's do this the other way. So I'd like to talk about transformations of random variables for a second. But what we want to say is that if the factorization exists, then Tx is a sufficient statistic. So let's go through that. So if factorization exists, which factorization f of x given theta is equal to hx g tx given theta, then Tx is sufficient. So if you can factorize it, then it's sufficient. And that's what I'm doing over here. I'm just imagining I can factorize it. I'm seeing the factors and the things I can't untangle from everything, so it's telling me what the sufficient statistic is. So when I just eyeball the formula, they go, that's sufficient. It's because the formula is relatively simple, and I can do the algebra in my head and do some factorization. Of course, for big hierarchical models, it can be difficult to tell what the sufficient statistic is. So you don't always know. I want to use an example to tell us what's going on here in this proof. be bouncing back and forth between the proof and the example really quick. So example, just imagine I've got 2 dice. 1, 2, 3 things here. So this is just a standard die. And I'll call it just die 1. So I'll just call this D1. And I'm going to have another dice, another die. So let's see. So this is another standard, but we're going to call this standard die 2. I'll just give this a name. What I'm going to do with these is I'm going to roll them. Each one of the faces will have probability 1/6, so these will be fair die. So each face has prob 1/6. That's what I mean when I say they're standard dice that I'm rolling. What am I going to do with these 2 dice rolls? I'm going to add them together. So I'm going to roll these dice a number of times. So I'll call the index 1, or index I. We're just going to do it once, I think. And I'm going to add it to this. So this is just the sum of 2 dice. So very simple sort of probability problem. This is probably the sort of stuff they were studying when they concocted probability. So all this stuff generalizes. Okay, we're going to come to this example in a moment. I think we understand this example pretty well. This is probably where we learned about conditional probabilities and joint probabilities and wrote out a contingency table and all the possibilities that contribute to sums. Let's just write this down. So if the factorization exists, then T of X is sufficient. So to verify something is sufficient, I want to show some ratio as a constant with respect to its parameters. So I'm going to look at, I'll say F of X. Bless you. Bless you. And I'm going to call this Q T of X, given theta. So the book is chosen to be polite for the first time, where they end up distinguishing that distribution from that distribution. So we're just going to be careful in our notation about what distributions. Usually I just write down something down here and tell us what the distribution is, and it usually looks just like that random variable. So we'll use F and Q. So our goal is to show that this ratio is a constant with respect to theta. So I get to use this in the proof. So that the factorization exists, I want to show Tx is sufficient, so I want to show that this thing is constant with respect to theta. So this looks like this. This is going to be G T of X given theta, i.e. the stuff that I can't untangle from theta is the sufficient statistic. We'll show that that's sufficient in a second. So the factorization exists, so I can immediately factorize that. And this is probably the most confusing part of the proof, is they write down this thing like this. Give you some set notation. This is going to be y's. This is going to be a sum over all the y's such that, so the bar always means such that some condition is fixed. So the bar has the same meaning as the bar that I like to invoke when I describe a likelihood function or a conditional probability. It's telling me some condition is fixed and it never is untrue. So I'm going to say T of X is equal to T of Y. Right here. So this is observed. This is fixed. So that is our sufficient statistic that we've computed in the first place. And they end up writing in right here, this is F of Y given theta. I'll write it in that way. So let me explain what this means. So I think this is where most people get confused. So this right here, this whole condition is under my summation sign. So what I'm going to do is I'm going to collect a set of y's such that that condition is true. And out of that collection of y's, I'm going to sum over all of those, where I plug y into this original sampling distribution. Let me remind you, this is probably the way we learned about transformation of variables. And I'll explain this through this example right here. So I don't need to transform the distribution and come up with its transformed distribution. I can look at the original underlying distribution. That distribution is f right here. So I can look at the original bit. So I don't have to look at the sum of the two random variables. I can think about all the possibilities of the original dice and think about their probabilities, and that's what leads to the probability of the transformed random variable. So let me just ask this question. So let's say this is 7. So there's a concrete example. This is probably the worst example I could come up with, because this has the most possibilities. So say this number is 7, and I want to come up with a probability of this. So we want the probability of the transformed random variable. In our case, that's the sum. And we want the case where it's equal to 7 itself. So what I can do is I can think about all the different possibilities from these two different dice and add them together. So all I have to do is enumerate all the possibilities. I've got dice 1, I've got dice 2. So this could be a 1, and this is a 6. This is a 6 and a 1. This is a 5 and a 2. This is a 2 and a 5. I've got a 4 and a 3, and a 3 and a 4. Any other possibilities? I think I got them. There's no 7 and 0 to add together. So now I just need to enumerate the probability of all of these different events happening right here. And they all happen with probability 1/36 because of the uniformity of the die. And there's a certain number of ways that I can add this together. So I've got 1, 2, 3, 4, 5, 6 different ways. So this is the highest probability event that you can see in this case. So the probability is the sum of all of these possibilities. So these all happen each with probability 1/6 times 1/6. Again, I'm going to the original probability of the dice, and I'm not really working through the transformation explicitly and coming up with a formula for that. I could do that, write down this distribution and just answer the question, or I can think about the original distribution and add together all the possibilities. So that's what this means. So once I sum over all of these things, I have a sum of 7 or 6 of these things. I add that up, and that's what that sum is doing. So hopefully you understand this notation now. Again, I can go back to the original distribution, think about the probabilities of those elements, such that they add up to something that's fixed. So this is the fixed condition right here. So this would be the 7 in this example. And now I'm just summing over all the different possibilities that give me 7. That's what's going on there with that notation. This is a discrete example that they wrote down in the book. If x was continuous, this would be an integration sum. Does that make sense? So that is the definition of, maybe the definition of a transformed random variable.
So the transformation, we'd have to worry about the Jacobian, if we're continuous, but
right.
Just 1 in that case?
In a discrete example, it's always 1. There is no Jacobian.
If that were continuous, though?
Yeah, then you would need a Jacobian.
Okay.
Right, and do everything. So we can't, but I could still integrate over the original stuff and add it all in. Or you can do it the way that you're used to and derive that distribution and just compute its probability. So 2 different ways to do the exact same thing. And in that, if it were continuous, and I was just trying to derive this distribution, then I would do the Jacobian. Does that make sense? Okay, so they say in the book, this is because that's the definition of a transform random variable. And I remember looking at this for the first time and going, that's the definition, huh? So I don't remember it this way. And then I started thinking about it a little bit more and go, oh, this is the way they teach you in Stat 101 land. Does that make sense? Cool. So we're almost done. With this proof. So this is GTX. In the numerator, now I can sum over this set, where I've got some fixed condition right here. So all the y's that I'm going to be sampling out of it have to have this constraint, where it adds up to the constraint that we're given. So, and I can replace f of y with this factorization right here. So this is going to be h of y. This is going to be gt of y given theta. And so keep in mind, this is the constrained thing. For every one of these entries into the sum, this ty right here is fixed to be tx. So it is that number. So out of all those dice possibilities where we roll them, all of the entries that we summed up added up to the same thing, 7. So we excluded all the other ones. So I can factorize this thing outside of this because it's fixed. It's always fixed. It always has that constraint right here. This looks like this, GTX, given theta. Oops, sorry. There was an h of x up here. H of x. So this is going to be GTX given theta. So as soon as I factorize this out of the sum, I had to call it that fixed thing. So it's always all the ty's are fixed to be tx. Tx. Well, the ty. This constant bit is not fixed. So these y's could be all different possibilities of things. So I'm adding those things up with all the different possibilities of things. The important part, the part that's tangled up with the parameter, always has a fixed thing in there, and I can factorize it out. And so when we see the cancellation right there, those two things cancel each other. And then I'm just left with the ratio of these constants. So this is h of x divided by sum of y's, where I've got my constraint. I'll write it this way. Same exact thing. H of y. And so when we see this is not a function of theta. So that's that. Okay. Any questions about that proof? I think the only hard part is just that substitution down in the bottom of the sum and just understanding what they're talking about. So that is the definition of a random variable. So if you take a measure theory class, they'll explain a random variable to you not as, well, let's just kind of do something stochastic, probabilistic to it. That's a random variable. It's random. They give you a mathematical definition. It says that you can map back to the original elements in the problem and describe their probabilities. So in a probability space, you put the probabilities on the original elements in the problem before you transform. And if I can talk about what I've transformed and map back to the original elements and know what their probabilities are, then it's a random variable. So that inverse map has to exist. What is the inverse map in the dice example? If I wanted to sum two dice up to 7, then I've got the 1 and the 6, the 6 and the 1, the 5 and the 2, the 2 and the 5, and the 4s and the 3s. And I add up all those possibilities. So I can map that, and I can know what the probabilities of those events are. And so each one of those events is 1 over 36. So the probability, writing it down, is relatively straightforward. So all these super, like, technical definitions, usually there's a simple example that explains what it is. So I never try to prove anything until I understand things in the simplest terms possible. I think that's usually a good idea. You can almost build up all probability theory just by looking at step functions. And so that's what a measure theory class might be about. Okay, let's look at this example real quick. So if we're just thinking about a normal distribution, right here, I can factorize everything like this. So I can write down the joint distribution like that. I can rewrite everything like this. Usually I put that sigma outside of my square roots. Just be careful with that. So different people write it differently. So I've combined it here. I can write everything that way. I write it like this all the time. I know x bar has something to do with the problem, so I'm just going to squeeze it in there by subtracting out x bar and adding in x bar. It's just a funny form of 0. I'll just point out, every time you see the quadratic form in everything, so if you've got quadratic form and you want to know where it's centered at the average. So how many times do you have to prove it before you know it? So I'll just kind of point out that if I were looking at something like this, xi's minus f squared, and I wanted to know the arg minimizer. So the minimizer over f, the argument, what I would plug in for f to minimize this. This is just a calculus problem. So you can take your derivative with respect to f, set it equal to 0, solve for f, and what you'll get back is x bar in that problem. And so once you convince yourself of that once, and you want to know where this thing is centered, then you always know it's the mean. So anytime you see sums of quadratics, that thing is centered at the mean. If you want a general proof, just solve that problem. So that's how I know to plug x bar in. I remember this question when I was in college. How'd you know to do that? And so the professor says, well, I just know, because I've done it a zillion times and it always works out the same. So and that's the boat we're going to be in. So I can expand everything out into these terms, and I'll just pick up where I finished writing off here and complete everything. So f of x given mu. I just removed the sigma squared from this notation. If I saw this, somebody write this down, I would ask them, what did you do with sigma squared? Do you mean that it's constant and you're just not denoting it? It's in there, or did you integrate it out by multiplying by a prior and getting rid of it? I would need to know. But if I saw their formula on the right-hand side, I would know what the answer is. If sigma's in there, they're just not telling me about it because it's not important. Sorry for the inconsistency in the notation. I want us to just focus on mu. So this is 2 pi sigma squared to the minus n over 2. E to the minus 1/2. This will look like sum of the xi's minus x bar squared. I'll write this over sigma squared. This part, when I drag the sum across, so this middle term is going to cancel, so I'll just write it here, I minus x bar. This is going to be x bar minus mu. Right here, I goes from 1 to n. There's no indices here, so I can factorize that out. And so we can see that x bar minus mu, sum of the xi's minus x bar, is the important part of this term. And I'll let you work out, this is the sum of the xi's minus n times x bar. N times x bar is the sum of the xi's, so this whole term is 0. I usually do this, and I'll just write 0 there. It's not exactly 0 until I drag the sum over it. So this will be 0 after we sum over everything. I'm just going to remove that since I'm running out of space. So there's this extra 0 term. If you want to plug it in, you can. And then I'm going to sum this thing up. Again, there's no indices on that. So I'm just summing something up n times, so it's equivalent to multiplying by n. So this is n times x bar minus mu squared over sigma squared. And that's what that looks like. These things can be factorized. So this can be written as 2 factors. Minus n over 2. This is e to the minus 1/2 sum of the xi's minus x bar squared over sigma squared. And then I have this other factor, e to the minus 1/2 x bar minus mu squared over sigma squared divided by n. So I'll write it down like that. So I can never get rid of that mu from x bar, so I know x bar is sufficient in all of this. I'll just kind of point out the concluding part of this problem. So f of x bar given mu, this is this. 2 pi sigma squared over n, this is to the half power, e to the minus 1/2 x bar minus mu squared over sigma squared over n. So that is that distribution right there. We'll notice that this is this. And so when I take the ratio of these two things, those two parts will cancel, and that's the only place where mu exists. So I know that's a constant with respect to mu when I take that ratio. So that would be the formal way of showing everything is a sufficient statistic. And I'll probably ask you to recognize a sufficient statistic on the midterm. So I don't really care how you do it. You use the factorization in your theorem in your head, do it that way. That'll work for me. Or if you want to show the ratio and show that it's a constant, that will also work. I think they're equivalent. And that's what our proof tells us. Let's dwell on this for a minute. This extra term. This doesn't have a mu in it, but if I were thinking about sigma squared as a parameter itself, so if I change this problem into thinking about sigma squared, I'd immediately know this is the stuff that we can never factorize away from sigma squared. So no matter who's evaluating sigma squared or doing some estimate on it, they should be using this function. Now, how you normalize it, divide by n minus 1, n minus 2, we need some additional properties to talk about which specific version we're using. The important thing is that you're using that function to estimate it. So if you use some other function of the data that isn't equivalent to this, you can be beaten. You will be beaten. So if you're not using your sufficient statistics. So I'll point out also in the 2 experimenter problem, what they're looking at is the 2 experimenters, what the experimenter 2 needs to sample from is this thing. So this is part of the constant that he can figure out when he comes up with the ratio of these 2 different distributions and comes up with that conditional distribution. These parts will cancel each other, and I'm going to be left with some normalized form of this. So experimenter 2 needs to sample from this distribution in that example, which is not uniform. And it's a really funky distribution. And so I'll point out it looks like it's normal, but it's not normal because the xi's have to, the average of the xi's has to be x bar. So it's guaranteed to be in that distribution. And so when I was thinking about this, I was like, okay, this is a cool example that precedes the definition of a sufficient statistic. And I just read through the 2 experimenter proof, and they're telling me experimenter 2 knows how to sample from this thing. I doubt it. You know, what year did experimenter 2 live in? So how do they sample from this distribution? So this would be experimenter 2's distribution. And the answer that I'm going to give you is Metropolis Hastings. So that's our whole recitation section from the last 2 weeks. It's focusing on that algorithm. So after the midterm, what I'm going to give you is an extra credit problem where you can do Metropolis Hastings on that early problem with the t and the normal. And then I asked you to kind of modify the proposal in a particular way and make that problem work out. And there'll be a third part to Metropolis Hastings, and it's a sample from that distribution. And the name of the game is, how do you create the proposal? And so that's the only thing. So that's the question you can ask me later, is how do you concoct that proposal? I'd really appreciate it if you thought about it for a little while and came up with some clever schemas for coming up with it. But we don't have to be overly clever. I'll eventually tell you the answer of how I would do it. And I'll tell you other ways of doing it and what the relative pros and cons are. So I'd probably do something relatively simple because I could code it up. And I don't really care if the code converges in 30 seconds or 29.2 seconds. So it wouldn't make that much difference for the homework problem. So we'll come back tomorrow evening and do yes, no, maybes on the midterm. But I will give you a chance right now. So I know we're over by 2 minutes. Keep in mind I'll give you Monday off following the break. So you'll get a little bit of that time back. I don't think that I've given you enough time back yet, so I'll give you another day off too, when we can use it the most. Does anybody have any pressing concerns about what's going to be on the midterm? You can warm up one more time for tomorrow's yes, no, maybe. I got one. Sufficiency. Yes. I'll ask some question about sufficiency there. So, babies. Probably. So I haven't written the exam yet, so I'm not sure. So I'll try to allude to what the question might be. So again, this isn't here to shock and surprise you. It's just to motivate you to study.
So you can't say you're not expecting this stuff.
I'm not going to do that this time, just because we did have the proof this time. I just find it to be too rude to present something the day before a midterm and how you do it. So I think I won't ask you to prove the factorization theorem, and I'll probably ask you to do it on midterm too. So one of the easier problems. Give you something that, oh, proof, and it's this easy proof, great. So I don't want to just proof you to death in this class. So again, I will ask you one of the 2 proofs, either for the delta method or CLT, and I haven't decided yet, and I probably won't tell you exactly which one we're going to do, but it's going to be one of them. Cool. Thanks, y'all. Hopefully I'll see you tomorrow. Spring break, which is amazing. So we'll get to recover. Monday off following that, so we get an extra day to drive back. And then we're going to crush chapter 6 and chapter 7, and that's going to be the bulk of the stuff. And if I need time, I'm going to pull it out of chapter 8. So, because chapter 8 annoys me. So I just don't like hypothesis testing. I cannot conceal that. So we'll talk about why when we get to chapter 8. I think that's an important thing. Sometimes I'll do it, but I'm always super reluctant. I like the theory. I like what Nathan Pearson told us, and I think it can be used. I think there are useful applications. If you're doing quality control and you're really in a frequentist regime, and you're repeating the process over and over again, I think it's useful. Then shielding yourself from error rates means something to me. So, but I think in general, it's kind of silly. So for an observational type study, I think it's totally useless. So, okay, you get a small p-value, you can get somebody to accept your paper, but you end up coming up with a p-value that's obnoxiously small, you reject, and somebody says, yeah, but the hypothesis is just a whisker away from what you hypothesized about. So why are you saying it's so terrible of an answer? So that conversation. Okay, we'll stay unannoyed all the way through chapter 7. I think that chapter is lovely.